Hello all, I am Hari Vignesh and together with my teammate Ashwin, we are going to talk about the exploration versus exploitation dilemma. We mainly look into the multi-arm bandit problem and discuss about the various algorithms to solve it. So why did we choose this topic? Exploration versus exploitation is one of the hot topics in both academic world and the industrial world right now. From state-of-the-art R algorithms to a simple A/B testing, everything comprises of this exploration versus exploitation dilemma. We chose multi-arm bandit problem as it is one of the classic problems where we have the problem of whether to exploit or explore at any given point. Given the math heaviness of this topic, we tried our best to distance ourselves from the underlying math so that the presentation is not too complicated. Okay, so what is this multi-arm bandit problem? Imagine you are in a casino in Vegas and there are some N slot machines before you. Obviously, the amount of money that you might win is different for different machines. As a player and as a normal human being, you want to win the maximum possible money out of these machines. But now comes the problem. Which machine to choose? Let's say by playing the nth machine, you will receive the maximum money. But how will we know that the nth machine is your ideal machine? We don't know this. And we will usually end up doing any one of the following two things. Either we would have picked a machine and played in it till the casino closes, or for each time we might have chosen a machine at random and played on it. If we had chosen the first option, we might have won some amount, but we will never know the odds of winning by playing the other machines. If we had played a random machine each time, we will know that the odds of winning in each machine, but for sure we would not have won the maximum money possible. This is the general problem behind all the exploitation versus exploration problems. There are quite a lot of applications for this, and the famous ones are like the A/B testing, investment analysis, and reinforcement learning. In A/B testing, all the candidate websites become slot machine, and each time when a customer comes, you have the option of showing one ideal candidate to him such that it increases the probability of him buying something from your website. So which one to choose? Which website should we show to him? That's the problem, same as the multi-arm bandit problem. Again, if you take the reinforcement learning, rewards are given based on the action a learner takes. The learner must discover on its own which action it should take, and it should also learn from its experience. At any given point of time, the learner at a state T has some n possible states to which it can go. So, which state should it choose to maximize the reward? Again, it's also a multi-arm bandit problem. Now let us see the mathematical definition of the multi-arm bandit problem. A bandit can be considered to be a tuple of A, R, where A is a set of possible actions and R is our reward function. Let's say we have some n reward probabilities. For a Bernoulli bandit, then at each time t, we take action A from the set of possible actions, and the reward function R may return 1 or 0 based on the interaction of our action with our chosen state probability. For our slot machine example, the n reward probabilities are the n slot machines with varying win probabilities, and the actions are our interactions with these machines. At each time step t, we take action A on one of these slot machines and receive a reward R. R can be 1 or 0 based on the slot machines we chose. From the previous slide, you might have guessed that we need to increase the reward R. That's right. For getting the maximum money or profit, we need to increase the total rewards or decrease the total regrets we get. Rewards or regrets is the parameter we are more concerned at the end of the day. Total regret is calculated as, for the total actions taken till time t, the sum of the difference between the optimal reward and the reward got using that chosen action at that time before t. But the problem is, we don't know which is the optimal action. Without knowing it, how can we calculate the maximum reward? All the algorithms that we are about to see from now on will try to solve the multi-arm bandit problem by using some greedy heuristic or some bounds so that we might get a maximum reward. The first is the naive greedy approach. Let's take the slot machine example again. Let's assume we have some 4 slot machines and we have around 500 turns till the casino closes. In greedy approach, you spend around 100 trials in each slot machine to find the average win probability of each machine, and for the last 100, you pick the one with the maximum average probability. In general, at each time t, you estimate the value or reward of all possible actions using Monte Carlo method, and you pick the action with the highest possible reward as the next action. So what are the possible drawbacks of this method? You might get stuck with a local maxima instead of a global maxima. You waste a lot of chances by playing with machines with guaranteed low rewards. Because of these drawbacks, the greedy algorithm has proven to have a linear total regret. That is, as the time on trial increases, the total regret tends to increase. Next is the epsilon greedy approach. In this, we take the best possible action most of the time, but also does a random exploration occasionally. That is, we continue to explore forever with the epsilon probability, and we exploit with 1 minus epsilon probability. In terms of our slot machine flag, we choose a machine randomly with epsilon probability and exploit a particular machine with 1 minus epsilon probability. Once we start to recognize the best possible machine at a particular time t, we start to exploit that more frequently with 1 minus epsilon probability. Keep in mind that we still explore other machines with epsilon probability. As the time goes by, some other slot machine might seem more profitable based on our experience, and this algorithm can identify it, and we will start to exploit that machine with 1 minus epsilon probability from there on. This is one of the key features of epsilon greedy approach, and because of this, we will not get stuck in a local maxima itself for a long time. A typical epsilon value is around 0.1. For example, like if we have around 10 slot machines, then for around 1% of the time, you randomly choose a machine. Rest of the time, you exploit the best possible machine at that point, which is pretty good in compared to the name greedy approach we already saw before. Even though epsilon greedy seems to be a good choice, it has also been proved to have a linear total regret. There are 2 more famous variations of the epsilon greedy approach. First is the decreasing epsilon greedy approach. In this, you reduce the epsilon value gradually over time. So, why to do this? What's the use of doing this? Usually for problems like these, exploration is very much needed only at the initial stages of the problem. As the time goes by, usually we would have narrowed down on our search for the best possible outcome, and hence we need to lower the number of times we explore and considerably increase the time we spend on exploiting the best option. R algorithms have proven to show a much more faster convergence by using a decreasing epsilon greedy approach rather than the normal method. The next is the context-based decreasing epsilon greedy approach. In this, we decrease the epsilon value based on the relevance of it on time. In this approach, the epsilon is more tunable and hence widely used in time-critical applications. One good example is A/B testing. For example, like during a festival season, once you have marginally narrowed down the best candidate website, it's better to stick with that, as failing to do so might result in the revenue and the customer loss. And these varieties of greedy approaches have logarithmic total regret, which is much more efficient than the linear time total regret of the previous approaches. Hence, these are widely used in many of the exploitation versus exploration problems.
Till now, we were looking on when to explore and when to exploit. Now, we are going to make a decision on what to explore and how optimize you can explore. So in a greedy approach, you make a random choice of exploration. This can be bad and it's of no use if you already know the options you're going to explore are bad choices. So how do you make a decision if it's a bad choice and when you need not explore that option? So that's where the upper confidence bound comes into play. So you explore an option which has a maximum gain and you try to build a confidence out of it. So that's where the upper confidence bound comes into play. And this is a more optimistic approach, expecting the maximum gain to give you maximum rewards. But this could also be a bad in a friend, that what you're trying to explore might have the maximum gain but might not have the maximum probability of occurrence. The best example for this would be a startup in a Silicon Valley. So if you join a startup in Silicon Valley, you have a possibility of being in the lower range of startups or being the next Google. So the chance of you being the next street startup is more probable than you being the next Google. So this works in an environment where the systems are less forgiving to errors, and it doesn't impact a lot immediately, and it runs better on the longer run.
One of the algorithms that works for upper confidence bound is by utilizing Chernoff-Oftings inequality. What is Oftings inequality? Given a random variable z and its expectation e of z, how close is the variable z with respect to its expectation is given by Oftings inequality. I'm going to spare the details on the math inequalities and they use the result in UCB's algorithm. So UCB is like a cluster of algorithms founded by Orr and its team in 2002, and UCB1 is like the primitive algorithm they came up with. So the idea for UCB1 algorithm goes like this. Start by playing every arm at least once so that you get a distribution of for each arm. Then figure out which machine could be the best possible one based on a statistical level of confidence and play that machine as much as possible. There are two ways a machine could be the best. You have measured its mean payout to be higher than the payouts of other machines and you're certain about this. Or you have not measured the payout very well and you're not very confident about it. So if you look at the equation is like this. So the empirical mean of utilizing arm I at time t is given by the previous empirical mean at time t minus 1 added with a factor of ln of t divided by the number of times the arm was used and square root of that. So if you look at that, the first part gives you like the exploitation phase. You're selecting what was the best in the previous state, you're trying to use it in the current state. And the exploration phase is where you're trying to explore an option that was used least number of times. If you look at that exploration factor, the n of I gives you like the number of times arm was used, and since it is in the denominator, if it is small, you'd be exploring more number of time. Since the mean is given as a sum of these two factors and these two factors counteract each other, they try to form an equilibrium. Then you'll be selecting an arm which has a maximum empirical mean, and then also at the same time you'll be incrementing n of I. The good thing about using Oftings inequality is that it is lower bounded by log of t. And UCB works very well when it comes to a large data set. The next upper confidence bound algorithm we are going to look is the Thompson sampling method. A little bit history on Thompson sampling. So Thompson was a pioneer in asking the question of exploring versus exploitation. He was attempting to do a clinical trial where you'd give his patients both a placebo pill and a effective pill and try to measure how effective the pill was. So the problem here is the pills are effective only after a month, or it takes a lot of time for the pill to show its effect. But he didn't want to waste his time by exploring the effectiveness by waiting for the effectiveness to show. So he suggested an idea of sampling a method so that you can explore and exploit with a certain possible probability involved in it. So in order to understand that, we need to understand what beta distribution is. Beta distribution can be given with two parameters, alpha and beta, and they define the distribution, and it is commonly used in Bernoulli experiments. So alpha is going to denote all the successful atoms and beta is going to denote the unsuccessful atoms. I'm not going to go detail into how beta distribution is derived, but in a numerical aspect, when alpha is equal to 1 and beta is equal to 1, it's going to follow a uniform distribution. And mean for a beta distribution is calculated by alpha divided by alpha plus beta. So in the first case, the reward probability is going to be 50, but since the values of alpha and beta are very less numerically, the final result 50 is not going to be as confident as the second example. In the second example, the reward probability is going to be 10, and since alpha and beta values are larger compared to the previous example, it's going to be more confident. Another use of using beta distribution is, given a prior and you want to do an experiment, and you can use beta distribution to calculate the posterior after the experiment.
So let's look at Thompson's algorithm with the respect to answering the question exploration versus exploitation. So for this, you need to keep track of two things for each arm: the number of times an arm was successful and the number of times the same arm was unsuccessful. So the algorithm goes like this. For every instance of time t, you generate theta of t for each arm using the beta distribution. So the beta distribution has two parameters, alpha and beta, as we discussed. So the alpha is the success rate. So it constitutes the success rate of that particular arm. And if the current trial is successful, the indicator variable will turn true and it will constitute for the reward. And if the particular arm was unsuccessful, the indicator variable in the beta phase will turn true and it will be 1 minus the reward. And then you'd select an arm which has a maximum theta of I, and you'd go on doing this until you reach an equilibrium. So theta of I constitutes the empirical mean, and as the time progresses, it will move towards the real empirical mean. And this is where the algorithm converges. Okay, let's see some graphs that explains why Thompson sampling does better in time compared to the greedy algorithm. So Russo, Daniel, and his team came up with this paper on tutorial with Thompson sampling, and they created environments to run simulated tests on various actions and paradigms, and it's very interesting. You can have a look at the paper. We have taken a simple example and trying to explain this. So they have taken a space which has three possible actions, and green action is the best possible action you could ever take in that system. So as you can expect, greedy immediately chooses the best possible and sticks to it and doesn't change. But at the same time, it still has a possibility of 25% or between 25% of choosing either the red or the blue action even as the time progresses. But with Thompson sampling, uh, it, it immediately chooses the green action, but you can see that the confidence of the green action keeps on increasing over time, and eventually it rests as one, and there's no more exploration of the bad actions, the red and the blue. So this eventually explains that Thompson sampling is better for something that goes over time, and it also reaches a convergence state where you need not explore any bad options. Okay, now let's look at some of the real world applications of this algorithm. We have seen it is used in A/B testing, reinforcement learning, and a lot of other technical stuff. But I feel this can be an example of what can be used in real life. So when we are young, we have an opportunity to explore a wide variety of fields. We can try sports, cinema, and science, math, and whatever we feel good at, we try to exploit it. As and when we exploit it, we are still exploring new hobbies related to that field or maybe the old field. But as soon as we start to turn 50, 60, we try to settle down and we just exploit whatever options we already chose when we were young. This is an example of decaying in time epsilon greedy approach. Another example of using an upper confidence bound is where venture capitalists try to invest a lot of amount uh, on a potential startup. So when a startup is evaluated at $10 million, venture capitalists try to move towards that rather than moving or exploring options which are at $1,000 or $2,000 evaluated companies. So this shows us that we are already using exploration versus exploitation without intuitively knowing what it was initially. And of course, we can use this in our slot machines. And next time you're in Vegas, you need not use luck. You can use greedy approach. So these are some of the papers and online references we used for this assignment. And if you still want to discuss something about exploration versus exploitation and how it is useful, feel free to comment in the PRs post. Thank you for taking your time.